Good morning, all of you. My name is Aikira. I'm your chemistry lecturer. If you remember, in our last class, we discussed de Broglie's wave theory and Heisenberg uncertainty principle. Today, we shall be discussing about quantum mechanical model of atom. Before going to actual topic, let's discuss some introduction about this model. Before this model, we have different models. That all models we discussed in previous classes. That all models are proposed based on classical mechanics. Classical mechanics. Now the question is, what is this classical mechanics? This classical mechanics was developed based on Newton's laws of motion. This classical mechanics mainly deals with the study of particle nature. It perfectly explains the particle nature of macroscopic particles. For example, moving car, falling object, motion of rotating planets, etc. It was perfectly explained the macroscopic particles. We know that macroscopic particles, the nature is particle nature. The wave nature of macroscopic particles are negligible, so we are not considered. In case of microscopic particles, it has dual nature, particle nature as well as wave nature. These classical mechanics failed to explain the dual nature of microscopic particles. In order to explain the microscopic particles, the dual nature of microscopic particles, the scientists Heisenberg and Schrödinger was developed one theory that is called quantum mechanics. It is a branch of theoretical science. It deals with the study of motion of all microscopic particles and macroscopic particles. They completely explain the dual nature of all microscopic particles like electron. Based on this quantum mechanics, one model was developed that is called quantum mechanical model of atom. The fundamental equation of quantum mechanical model was given by Schrödinger, that is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square e minus v into psi is equals to 0. Here m is the mass of electron, h is Planck's constant, E is the total energy, the sum of potential energy plus kinetic energy. V is the potential energy of electron, psi is wave function, and these x, y, z are coordinates in three-dimensional space. This equation is called Schrödinger's wave equation. This equation is developed based on de Broglie's wave theory and Heisenberg uncertainty principle. This equation is also expressed as h psi equals to E psi. Here, h is the Hamilton operator or mathematical operator, E is the energy, and psi is called wave function. This equation explains the behavior of moving electron in three-dimensional space. Now come to the important features of this model. According to this model, the energy of electron is quantized, which means the energy of electron can have a fixed values. And it explains the probability of finding electron around the nucleus in three-dimensionally. Let's understand. This is nucleus and this is the probability of finding electron density around the nucleus in three-dimensional space. It explains the probability of finding electron around the nucleus in three-dimensional space. According to de Broglie's, electron associates some wave nature like this. This wave nature, wave properties can expressed as a function that is called psi. Psi is called wave function. The psi contains all the information about this electron, all the information about moving electron. That is the energy of electron and the continuous motion of electron and the volume of the electron density. That all information contains this wave function that is called psi. For example, in the first orbit wave function, This Hamilton operator operates on the first orbit wave function. We get the energy of the first orbit wave. Similarly, in the second orbit, if I take second orbit wave function, this Hamilton operator operates on the second orbit wave function. We get the energy of the second orbit wave. Similarly, third orbit, fourth orbit, fifth orbit. So this psi have different values, and psi it also have positive values and negative values. Psi is equals to sometimes positive values and also negative values. There is no consistency on these psi values. For that, one new function was introduced, that is psi square. Psi square. It is called probability function. Probability function. We know that we cannot find the exact position of electron in an atom. For example, electron is present here, electron is present here, electron is present here. We can't find it. We can find only the probability of finding electron at different places in an atom. For example, maybe electron is present here, maybe electron is present here, maybe electron is present here, like that. This probability function gives the information about the maximum probability of finding electron at a certain point in an atom. That is called probability function. That particular point is called orbital. It is represented as like this. The new term orbital was introduced. The orbital is nothing but the three-dimensional space around the nucleus where the probability of finding electron maximum. That is called orbital. For example, this is the nucleus and this is the electron density around the nucleus. This region, probability of finding electron is maximum. So this is called orbital. And one more important point. Now let's assume electron is present here. The distance is r. The probability of finding electron a certain distance from the nucleus is called radial probability. That is indicated with r. These are the important features of this model. The graphs related to psi versus r, psi square versus r, and nodes, nodal branes, that are we will discuss in next class. Now we will come to the next topic, that is quantum numbers. To describe the position of an electron, 4 quantum numbers are required. They are principal quantum number, and second one is azimuthal quantum number, and third one is magnetic quantum number, and fourth one is spin quantum number. The 4 quantum numbers are used to locate the exact position of electron. Let's discuss one by one in detail. The first one is principal quantum number. It was proposed by Niels Bohr. It is denoted by letter M. The n values are 1, 2, 3, 4, and so on, or K, L, M, N, and so on. Let's understand. This is the nucleus, and these are orbits or shells. For this, n is equals to 1, this is 2, this is 3, this is 4, and so on. Similarly, this is K shell, L shell, M shell, N shell. It describes the size and energy of the orbit or shell. As n value increases, the size and energy of the orbital shell increases. The maximum number of electrons present in an orbit is equals to 2n square. And the angular momentum of electron is equals to nh by 2 pi. This is the principal quantum number. Now come to the second one, azimuthal quantum number. It was proposed by Sommerfeld. It is denoted by letter L. The L values are 0 to n minus 1. That is 0, 1, 2, 3 and so on n minus 1. It gives the information about subshells present in the main shell. We know that principal quantum number gives the information about shell, main shell. This azimuthal quantum number gives the information about subshells present in the main shell. For example, this is nucleus and these are main shells. In this, subshells are present. For example, n is equals to 1. This is n is equals to 1. This is 2. This is 3. N is equals to 1. L value is equals to 0 to n minus 1 and 0 to 0, 0. Every L value represents a particular subshell. This L is equal to 0 represents S subshell. And this have one subshell. Similarly, n is equals to 2. L is equals to two values. One is 0, another one is 1. 0 represents S subshell. 1 represents P subshell. And n is equals to 3. L represents three values. One is 0, 1, 2. 0 represents S subshell. 1 represents P subshell. 2 represents D subshell. If in case 3 represents F subshell. And this azimuthal quantum number also gives the shapes of orbitals. For example, let's understand. In this n value 2, it has two subshells. Like this. In this n value 3, it has three subshells. Like this. And it also gives the shapes of suborbitals. Let's see. The shape of S suborbital is spherical. And the shape of p orbital is dumbbell. The shape of d orbital is double dumbbell. The shape of f orbital is four-fold dumbbell. And the number of subshells present in the main shell is equals to the n. For example, the number of subshells present in the main shell is equals to n. N is equal to 1, one subshell is present. N is equals to 2, two subshells are present. If n is equal to 3, three subshells are present. So the number of subshells present in the main shell is equals to the n. And the angular momentum of electron is equals to h by 2 pi common into root of L into L plus 1. This is called angular momentum. This is the azimuthal quantum number. Now come to the third one, magnetic quantum number. It was proposed by Landé. And it is denoted by letter M. The M values are dependent on the L values. M values is equals to minus L to 0 to plus L. For example, N is equals to 1, for that L is equals to 0. M values is equals to 0. Every M value represents a particular orbital present in the subshell. It gives the information about orbitals present in a subshell. That is equals to S orbital. And for n is equals to 2, L values have 0, 1. For 0, m is equals to 0. It represents S orbital. For 1, m is equals to minus 1, 0, plus 1. It represents P orbital. It is nothing but Px, Py, Pz. For n is equals to 3, L have three values 0, 1, 2. For 0, m is equals to 0. It is S orbital. For 1, m is equals to minus 1, 0, plus 1. This indicates p orbital. For 2, m is equals to -2, -1, 0, +1, +2. It indicates d orbital. Here, this is dxy, dyz, dzx, dx square minus y square, dz square. These are orbitals, d orbitals. The maximum number of orbitals present in a shell is equals to n square. And it gives the information about orientation of orbitals in space. Orientation is nothing but arranging in a particular direction. And the number of orbitals present in subshell is equals to 2l plus 1. The number of orbitals present in a shell is equals to n square. The number of orbitals present in a subshell is equals to 2l plus 1. The maximum number of electrons present in an orbital is equals to 2 into 2l plus 1, because the orbital is represented like this. In this, the maximum number of electrons accommodated is 2. In this, maximum number of orbitals is 2l plus 1. Each orbital has filled 2 electrons. So, multiply with 2, we get the maximum number of electrons present in a subshell. This is the magnetic quantum number. Now come to the fourth one, spin quantum number. The first three quantum numbers, principal quantum number, azimuthal quantum number, magnetic quantum numbers, are derived from Schrodinger's wave equation. The spin quantum number is independent. This was proposed by Uhlenbeck and Gaudsmith. It is represented as S or ms. The values are S values is equals to plus of, minus of. It describes the direction of spin of electron. That is, the direction is clockwise rotation. It indicated with plus of. The direction is anti-clockwise rotation. It indicated with minus of. The spin angular momentum of electron is equals to h by 2 pi into root of s into s plus 1. Here, s is equals to total spin. That is equals to n into half. Here, n is the number of unpaired electrons. Each orbital accommodates 2 electrons with opposite spin. This is also called spin pair. That's it today class. In our next class we will discuss nodes, nodal planes, graphs related to psi versus r, psi square versus r.